right, so we're going to finish up volumes here today, just with here at the beginning, and move on to some other stuff. So volume of a solid, any kind of problem that is volume of a solid is going to be one of two types. It's either going to be a revolution, rotating region that creates a solid, or it's going to be a base, right? It's going to be a solid. The region will be the base of the solid, and you'll have slices coming up off of that base. So it's going to be one of these two types here, okay? Now, if it's a revolution type of solid, a revolving region, then you have two ways of doing it. You can either do it with our slicing formulas, disc or washer, and this is kind of that's the term that is usually used for this, is disc. This is typically called the disc method. This is typically called the washer, and that just means if there's empty space or not. If your slices are circular slices, but either they're solid slices or they have empty space like a washer. So you're either going to do it that way, the slicing, and there the strips are always perpendicular to the axis of revolution, or we can do this new thing we learned called the shell method, which is 2 pi times p times h. P is from the center to the strip, and h is the length of the strip. And it's that easy. But the difference there is your strip is parallel to the axis of revolution. Parallel to the axis of revolution. Okay? So that can be an advantage. So when you have a region that's being revolved, you have that option of how to do it. If you have a solid that's on a base, you have no option. You're just going to do it by the slicing method. You're going to use one of these area formulas to put it. Okay, that's pretty much it. So, number 4, we have this region here. The P would have been 0 minus Y, because your strip would have been down here somewhere, like so. And so here's your axis of revolution. So 0, top minus bottom. So 0 minus Y, and the H would have been 2 plus Y. It would have been 4 minus the quantity 2 minus Y, but you can leave it like that. It doesn't matter. Okay? So, what was the answer on that one? 8 pi over 3. Okay? Next one we had was this region. We're revolving it around there, so our strip has to be parallel to that. So it looks like so. So if we label that as our y, the distance from there, that would be y minus 0. So what number is this? 9. So, or not y, I'm sorry, that's x. And so x, so the p would be x minus 0, and the h on this one is the height of that strip, and that would be that equation minus that equation, which is 4x minus x squared, 4x minus x squared minus x squared.
Wait, why is the px minus 0? I got 2 minus that. So.
4, 9. Okay. It's revolving around the y-axis, right? So that's your center. So the other half of this solid is going to be over here, right? It's going to be this kind of a thing. Okay, so P is how far that strip is from the center. So if this strip is here at 1, how far is it from the center? 1. If the strip's over here at 2, how far is it from the center? 2. If the strip is at 1/2, how far is it from the center? 1/2. So it's right minus left. It's right minus left. Yeah, the 2 wouldn't have anything to do with that. Okay, it's always right minus left. And remember, P is always going to be x minus 0, x minus 1, 2 minus x, 3 minus y, y minus 7, whatever. Okay, and the answer on that one was 16 pi over 3. Okay, number 12, we have this region here. Now, you were supposed to do this with shell. This would be easier with the disc method. Okay, why is this harder with shell? You have to split it because we're revolving around a horizontal axis. shell method has to be parallel to that. So the strips would be here. Well, right here, you're going to have to split it. So you'd have some up here, and you'd have some down here. Okay? P is that, so if this is, we call this Y, if we call the strips Y, because that, right? I mean, that strip is hanging out there at 0.5, or 0.3, or 0.4, or 0.7, right? I mean, the strip has a Y that's hanging out at some Y value. So that's why we label the strip Y. The distance from that strip to the center is Y minus 0. So P is going to be Y minus 0 for both of them, right? Top minus bottom. The top Y value is where the strip is, which is just Y. The bottom Y value is down here at 0. So P is Y minus 0. The length of the strip is going to change. In the bottom section, it's going to be what? 2 minus 1. Okay? In the top section, up here, the H is going to be what? What is this curve? Y equals 1 over X. So if you solve that for X, you're going to get 1 over Y. Is that right? Do I have the right equation here? Yeah. Okay. So it's 1 over, it's this X coordinate, which is 1 over Y minus 1. So it's 1 over Y minus 1. Okay? So, and of course 2 minus 1 is just 1. Yeah.
How do you know exactly when to split?
Well, because the strip always, and this goes back to when we were doing area at the beginning of chapter 7, the strip always has to touch the same curve on the right and the left, or the top minus bottom. Well, the strips down here touch 2 on the right and 1 on the left, but as soon as you get past this point, now the strips touch the curve on the right. So it's got to be split.
Well, I know that it has to be, and I know when to tell, but I just kind of.
Well, as soon as the strip stops touching the curve it's touching in the bottom section, so all the way here it's touching this line 2 until you get up to this point right here. Then the strips start touching the curve. So that's where you have to split it. As soon as it starts touching something different. Okay? This problem right here. We're supposed to find the area of this region. Okay? Well, if we draw strips in here, all of these strips are going to touch in the same place until when? Until right there. So we're going to have to split it right there. Because then the strips start touching here. Right? So we're going to have to split that into 2 parts. So we're going to do the integral from 1 to wherever that point is, and then from there to there. So it's the same idea. Same idea of what to split. Okay. All right, and so now, this, like I said, let me do this in blue. This would have been much, much easier to do just as a regular old disc. There wouldn't even have been any empty space, right? If we'd have done vertical strips here, we got a horizontal vertical or axis of revolution, slices would have been great here, right? Shell method is kind of a pain here, but we do it as a. So if on the quiz, if I don't tell you which method to use, and I just tell you take this region and revolve it around the x-axis, definitely do a disc method, right? This is going to be circular. There would be circular slices right there. This strip would be 1 over x, that y value. So that would be your radius. That'd be 1 over x minus 0. So this would be pi. And then it would be 1 over x squared. So pi r squared. Strips would go from 1 to 2. That would be what you'd want to do, right? But you couldn't on this one. You were supposed to do it with the shell method. So it would look like that. And the answer I got here is pi halves. Pi halves. Oh, and by the way, what is this point right here where they cross? 2 1/2, right? So your first integral would go, your bottom integral goes 0 to 1/2, and then the second integral would go 1/2 to 1. Okay? So P times H with a 2 pi out front. Don't forget the 2 pi out front. Okay, 17. 17, you are, again, revolving around, this time, a vertical axis of revolution, so we're going to want a vertical strip. We want it to be parallel. So this is one of those where it would be nice to do. It'd actually be pretty easy either way. So P would be what in this case? What's P in this case? How much? 6 minus x. Okay. H. Square root of x minus c. Right? And so there it is. Right? 2 pi times P times H. And the strips, the integral will go from 0 to 4. Okay? All right. So the answer, I've got 192 pi over 5. 192 pi. Okay, 21. Now we had various parts. Now in here, I think you had your option, right? You had your option to do it either way you wanted. So in part A, tell me disc, washer, or shell. Caleb, what'd you do on 21A? The shell. Okay. Macy, how'd you do 21A? Shell. Okay. Emily, how did you do 21A? You did shell. Okay. Did anybody not do shell on 21A? Or did you think you had to do shell? Thought you had to do shell. Okay. So Caleb, tell me which way my strip is going. Okay. I only care about 21A. It's horizontal. Okay. What is P on that? Y minus 0. What is H on that? Q root. Yes. So X would equal cube root, or Y to the 1/3. So 2 minus Y to the 1/3. What'd you get for 21? 128 pi over 7. Okay. Anybody do it? Nope. Nobody else did it with disc. You did it with the disc. Okay. Tell me what direction your strip is going.
From 0 to 2.
The strip, the vertical or horizontal?
Vertical.
It would have to be vertical, right? Revolving around here. And what is your radius?
X cubed minus 0.
Okay, and the integral goes from
0 to 2.
0 to 2. And Caleb, your integral went from 0 to 8, because this is 0.28. Okay, and do you agree with what he got? 128 pi over 7. Okay, Shay, how did you do 21B? You did it with the shell. Okay. You did it with a shell, revolving around the y-axis. Okay, which direction was your strip? So on B, did you do shell or dishwasher? You did shell. Okay, which direction's your strip on B? Yes. It's the same direction as this, right? So it would be here. Okay, what's your P value for 21B? Yeah. Huh? I'm sorry, say it again.
X minus 0.
X minus 0, correct. What's your H? Okay. Is that what you had, or you're just winging it as we go? Winging it as we go. Okay. Well, you're supposed to do C. And what's your integral go from? 0 to 2. Put P in there, you put H in there. And let's see. Logan, what do you have for an answer for 21B? 64 pi over 5. Anybody want to take a shot at this one with disc washer? I agree. Shell's a great way to do this one. That's how I would do it. But let's do this one with a disc washer. Somebody want to volunteer? So I'm calling somebody. Okay, Drew. Let's do this one with a disc or washer. What would it be, disc or washer? Washer. Okay. And so we need a big R and a little r, right? Oops. What would be big R? Matter of fact, here, draw it in. Draw the strip for big R. Oops. Nope. Radius always comes from the center. There you go. There you go. Nice. Okay, drawing little r. Nope. There you go. Always from the center. Good. Okay, Macy, what would I write down for big R? 2 minus 0. Okay. Casey, what would I write down for little r?
Little r?
Yeah.
It would be, what's the equation?
Y equals x cubed.
So it'd be x cubed minus
Horizontal strip.
Oh yeah, you have to solve for x. That equation, so plug in.
Will be x equals
The cube root of y.
cube root of 1, which would be y to 1. Okay. So little r. Another shot at it.
Y. 0.
Minus 0. Okay. So pi big R squared minus little r squared. And this, what would be the integral from what to what on this one? 0 to 8. Okay. Let's go to C. Okay. Shell, Maddie, or disc washer? How'd you do it? Okay. So what direction would be the strips? Horizontal. Right? So horizontal strips always got to solve for, right? So we have to do that. So draw in your big R for me. Because there'd be empty space, right? Good. Nothing else, you guys have a little appreciation for my drawing.
I didn't always want to.
Okay. All right. Allie,
No.
come on. So, what is, write down little r. What would little r be? Good. Yes, I just made those guys draw lines. You're actually right. Look at that. What would little r be? Right minus left. Remember, right minus left. So start on the right first. Which one of these is little r? This one up here or this one? Bottom one. So start on the right. So 4. There you go. Minus. Oop, oop. What's this one? What's this one touching on the left? 2. There you go.
That was a good save.
Nice save. Nice save. Good job. Okay. Nice save. Big R. Big R. Still 4 on the right. Minus. Yep. There we go. Now it would be this x coordinate. Y to the 1/3. Look, there's a 1.
It's a little one.
It's a little
It
one. We
works.
can see. We can see.
The 3 wouldn't go any smaller, so.
Okay, so 4 minus y to the 1/3.
And he just goes so fast.
Squared
So
minus
speedy.
2 squared. Just showing up. Just showing up. 0, 2, 8 again. Right? 0 to 8 again. Okay? But, and then that's fine. That's pretty easy. It was a pretty easy equation to get x by itself. So washer would have been just fine. But shell would have been pretty nice on this one, really. Cameron, what would have been my p? So it'd be this way. So Cameron, what's the p on if I was doing the shell? 4 minus x. Because here's the strip right here from the center to the strip, 4 minus x. Okay, what's the h? Height of the strip. So P would be that, H would be that. Okay? And D, revolving around y equals 8. Let's, Katie, how'd you do this one?
I did
the shell. Okay, so that would be horizontal strip, wouldn't it? Right? Horizontal strip. It's got to be parallel to the axis of revolution. So P would be, here's the strip right here. P would be from the center to the strip. That would be 8 minus y. Right? Because if that strip sitting down there at 1, how far is it from the center? 7. If that strip is at 2, it's 6 from the center. 8 minus 2. It's 8 minus y is P. H is the height of that strip. Katie? Y to the 1/3. So there's P, there's H. Easily done. If you're going to do big R, little r, here would be big R. Whoa, my goodness. Here would be big R. So much for showing. That's what happens when you get a little cocky. All right. Okay, big R. Big R, 8 minus 0. Little r, 8 minus x cubed. Okay. And again, this one would be 0 to 8. The blue one would be 0 to that. All right, get your notes out. That is it. Now, keep in mind, it is not May. What's your last day?
12.
12? Okay. It is not May 12th yet. It's April 12th. Actually, it is April 12th, isn't it? Oh, isn't that interesting? Okay. It's April 12th. It's not May 12th. We don't know how many days. You guys have any good count?
23 school days.
Oh, we'll give them on 22.
All right. So that's good. That's good. It's 22 school days. It's not 0 school days, right? You still got some school days.
Oh.
All right, here we go. Here we go. Okay. Moving on. Moving on. Okay, so yeah, if you've done this in physics, you at least understand the concept of what we're talking about here when we talk about work. Okay? Work is equal to force times distance. Force for us, for the most part, will be weight, measured in pounds if we're using English units. Okay? But it wouldn't have to be, doesn't have to be weight. We're going to do an example with a spring, the force. So we're going to talk about pounds of force moving a spring, and so that's not weight. But Okay, work is force times distance. So if I were to stand here and hold a 10-pound book, that's a heavy book. If I was to hold a 10-pound book and just stand here with it, that would not be doing any work. To hold 10 pounds is not doing any work. It has to move through a distance to be considered work. Okay? So, lifting a 10-pound book 7 feet off the ground requires 70 foot-pounds of work. So that's the units we use, foot-pound. Okay? Now, in science, you might use Newton meters, which is joules. Okay? Joules, J-O, I think it's Joules, that's equivalent to Newton meters. Newton is like pounds. Newton is a metric unit of force. Meters is distance, obviously, so you have Newton meters or joules. Most of our problems will be foot pounds. Most of our book uses, the problems we do will usually be in English units. So, okay, you'll see now. What's that? Work. Force times distance. Yes, it's called work. That's the name. Okay, now it could be inch pounds, right? I mean, it could be inch pounds or yard pounds, I guess, whatever the unit of distance is, okay? But feet is pretty typical, okay? So it's pretty simple. Now, in physics, much like most of the physics type of comparisons we've made, what's the difference between physics versus calculus is that is variable change. Okay, like in physics, when you've got all your position, velocity, acceleration equations, those all assume constant acceleration. So when you talk about average velocity, when you talk about those things, it's different than when we talk about it in here, because we talk about variable acceleration. We can do problems with amounts of change. Now, if you take a calculus-based physics, then you would have a lot of calculus equations in the physics, because then it would talk about the kinds of things we talk about with variable acceleration, for example. So what we're going to talk about here is we're going to talk about situations where the force changes throughout the distance. Okay? For example, we'll talk about, now technically, if I lift a 10-pound book off the ground, or a 10-pound weight, whatever, 10-pound weight, and I pick it up 7 feet, does that book or does that weight weigh the same when I lift it 7 feet high as it did on the ground? It doesn't weigh the same. Why not? It's farther from the center of the earth, right? Gravity is so the farther you get, just like when you're, at Mount Everest, you don't weigh as much at Mount Everest as you do at sea level, right? It has to do with gravity. Weight is a measure dependent on gravity. So technically, a 10-pound book on the ground weighs less once it's 7 feet in the air. Now, the amount is so small out in the, I don't know, whatever decimal place, that it's worth ignoring, and we do. So when we talk about a 10-pound book and lifting up 7 feet, we're essentially saying it's a constant force. It's still 10 pounds all the time. But that's the kind of situation. Just to give you an example of one of the situations we'll talk about is, say you had a well, and you lowered a bucket and put water in it, and you lifted that, you had a pulley or whatever, and you lifted or you just pulled up the rope and you pulled up that bucket, okay? Now, technically, as it gets farther from the center of the earth, it weighs less, but we're going to ignore that. But we're going to talk about a leaky bucket. We're going to talk about lifting a bucket where the water leaks out as you're lifting it, and by the time you get to the top, it's empty, which fat lot of good that did. But that definitely is a changing force, because now it's getting lighter as it comes up. And so the physics formula, that doesn't handle it. Okay? So we're going to need a calculus situation because there's amounts of change. Yeah. That's the second part of that, because when you're pulling, and like in a physics problem, you would ignore probably the weight of the rope. But you're right. If I've got 30 feet of rope out there, when I lift, the first time I pull it up, and then I grab the rope and pull again, well, now I've got a section of rope that I'm not lifting that I was lifting before. And then when I yank it up again, now I got another section of rope that I'm not lifting. So the rope is getting lighter also. So we're going to factor both of those things in. So if we were pulling up a bucket, even if it doesn't leak, we're going to have to factor in the weight of the rope changing. If it is leaking, we'll also have to factor in the weight of the water changing as well. Okay? And so we'll see how we'll do that. All right. But essentially, with a constant force, that is the equation, force times distance. Okay. We're going to start actually with a spring problem. Okay? We're going to start with a spring problem. Now, Hooke's law, now the F here stands for force. Okay? Hooke's law says that the force is directly related to, and K is called the spring constant, okay, the length that you've compressed or stretched the spring, okay? So when we talk about a spring, now what we're going to, you can think about taking a spring and squeezing it in from both sides or stretching it out from both sides, but essentially you'd have to add the distance you're going one way or the other. So to simplify it, we're just going to stretch it from a fixed point. So imagine we had attached to the wall here a spring, okay, and we were going to stretch it out from there, or we were going to compress it in. Now the force is the same either way, compressing in or stretching out. Okay, so it doesn't matter in the problem if we're stretching the spring or we're compressing the spring, it doesn't matter. And we won't have to worry about it, one's not negative or anything, we don't have to worry about that. Okay, we're just talking about how much work is done. Okay, so let's say we had a spring attached to the wall here that stretched out 3 feet. Okay, just a coiled steel, spring. So it's natural length. So you need to know at rest, how long is it? Okay, in this case, 3 feet. If we were then going to stretch that, pull that, and stretch it out to 5 feet. Now what happens as you pull the spring? It gets harder and harder the farther out you go, right? Until at some point you probably can't stretch it anymore. Okay, same thing with compressing it. It's easier at first, and then it gets harder and harder and harder as you go in to where you can't go in anymore. Variable force. Okay, the force required to stretch it that first foot is different than the next foot or the next foot. It gets harder and harder. And that's where Hooke's law comes in. Okay, depending on the spring, and different springs would have a different K value. It's called the spring constant, okay, which we'll have to be given information in the problem so we can find that. Okay, so for an example, here's something you'd be given in a problem. Okay, we got a spring, natural length is 3. Stretching it to 5 feet requires 10 pounds of force. Find K. So we would use Hooke's law. You're just going to have to memorize this. Spring problem. We're going to just do a couple of basic problems. We're going to do the rope and the bucket, and we're going to do a spring problem. And you got to be able to do both when it comes to the quiz. Okay, well, what would we do? Well, we'd plug the 10 pounds in for F, the force. K is what we're looking for. And what would we put in for X? X is the feet. We would not put in 5. We would put in 2. Because how far did we stretch it? 2 feet. It was at rest was 3, so that's like your 0. Right? Now, you got to read the problem. Because if the problem says we stretched it 2 feet, then X would be a 2. But it says we stretched it to 5 feet. So that means we stretched it from at rest to 5 feet. So we stretched it a distance of 2. So that X has to be the distance it was stretched or compressed from its natural length. Okay? All right. Well, or from its beginning. Like, for example, they might say, okay, at rest it was 3 feet, and then they might say well, no, they wouldn't. So anyway, so we get 2, and so K is going to be in this problem 5. So for that particular spring, our force equation is 5x. For that particular spring, our force equation is 5x. Okay? All right. So, here is the equation for the amount of work done. So, big F is the force equation, which we just found out in this problem was 5x. Okay? And then the dx stands for the distance. Remember how we said work was force times distance? Well, what we're going to do is the same thing we've done in a whole bunch of examples already, is the integral is like an adder. And the integral is adding up little bits of work. What we have to do, now think about this. if I stretch that spring a foot, how much work did I do? Well, the first 6 inches I did a certain amount of work. The second 6 inches were harder. Break it down even more. The first inch was easier than the second inch, which was easier than the third inch, which was easier than the fourth inch. You get what I mean? It's a changing amount of force the entire time. So it's like the slices. We do 6 slices. Well, they're not cylinders, right? We had to fudge that a little bit. Well, the same thing's true here. The first inch, it was not a constant force. First half inch was not a constant force. What about an eighth of an inch? You see what I mean? And what we're doing is we're the dx, the delta x, the change in feet, we're making littler and littler and littler, right? So we're using the integral to add up. We're calculating these little bits of work. You say, well, the first inch, it was pretty much the same amount of force, right? A little easier at the end of the first inch than at the beginning of the first inch, but, you know, pretty much the same. And so we can get the work in the first inch and the next inch and the next inch and then use the integral to add that up, right? Well, how would we get it exact? Well, we'd have to have those little bits of work go down to nothing, right? Just like our little dx or delta x always have. So that's why the dx ends up being work, okay? So when you think, or why this ends up being, in, for example, foot-pounds, because our force equation is going to be pounds and our dx is the feet. And that's why we end up with an answer that's foot-pounds. And the integral adds it up, okay? All right. Now, you can't really say what's the antiderivative of pounds, right? I mean, we've always done that in the past. We said, well, miles per hour, what's the antiderivative? Miles, right? Well, it doesn't really work in this case. So we've also talked about how you think of that dx as having units. In this case, it's like the little bit of distance that you're moving as that force changes. Okay, so for this particular spring, so to continue with this problem, you would be given this information down here. Now, it might not say find K, you just know you'd have to find K. So the problem might be this. There's a spring, natural length is 3 feet. We want to stretch it out to 5 feet, takes 10 pounds of force. How much work would be done in doing that? How much work did we do in moving it from 3 feet to 5 feet? Okay? How much work? So we would find K, find our force equation is 5x, and then we would go in our integral. We would put in 5x, which is our pounds, our dx is our feet, and the integral would go from what to what? 0 to 2. Exactly. 0 to 2. Go ahead and type that into your calculators. Is that right? 10 foot-pounds of work. 10 foot-pounds of work. Because now, you say, well, that's weird, because it was 10 pounds of force required to stretch it 2 feet. You'd think it'd be 20, you would think it'd be 20 pounds. Well, no, that 10 pounds is just at the end of those 2 feet. It took less pounds of force in the beginning, right? It takes 10 pounds to move it out to 2 feet. But it was less force in the beginning. So what was our total amount of work? It was 10, and that would be foot-pound. Okay? Now, what if the problem said, instead of that, what if the problem said, okay, natural length 3 feet, takes 10 pounds to move it out to 5 feet. How much work is done to move it from 5 to 7? Right? To keep stretching it. How much work would we do? So now we've stretched it out to 5. Now, how much work is done to move it out to 7? Would this change? That doesn't change because that's still based on the 10 pounds that were required there. So we've got our spring constant K for this problem. We've got our force equation. What would change? The integral would be, no, 2 to 4. 2 to 4, right? Because we're now out at 5, which is 2 from rest, 2 from our 0, and then we move it out to 7. So we moved it from 2 to 4. Okay? Now, type that in your calculator. What do you expect the answer to be? Bigger. Because now it's getting harder, so we're still only going 2 feet. Last time we went from 3 feet to 5 feet. Last time we went 3 feet to 5 feet, now we're going 5 to 7. What do you get? 30? And so you were correct. It is more. Because it's getting harder. So we're going the same distance as we did from 0 to 2. So we're only going 2 feet. But that force is changing and getting harder as we go. And so it's 30 foot-pounds of work. Okay? All right. That's pretty much it. That's about all you can do in a spring problem. You have to be given an amount of force needed to go a certain distance, and that's just this, a certain amount of force to go a certain distance. It's a linear relationship in a spring. That's what Hooke's law says. Okay? So K is basically the slope of that. It is the spring constant, and so you're going to use those two numbers to find K. So then that gives you your force equation, whatever K is times X. That's what goes into your integral. And then you have to figure out from what to what. Am I stretching spring? That's it. That's all the more difficult a spring problem can be. Okay? All right. Now let's look at this problem. The rope and the bucket. Okay, so we got a 5-pound bucket. We'll start here without there being any leak in the bucket. So we're going to have a 5-pound bucket. It's got 2 gallons of water that is raised 20 feet. The 20 feet of rope weighs 1.6 pounds. Okay? How much work is done in raising the bucket? So, think of it this way. So this is 20 feet. We're going to raise it. Here's the bucket down here. We're going to raise it up to there. Without the water. Okay? So, we're going to need to be given maybe sometimes they'll give you density, something like that, right? The density is the weight per unit of volume. Okay? So you can figure out what that would be. Let me see here. Okay. So in this particular problem, I think I've got that on a slide here. 16 pounds. So 8 pounds to a gallon. Okay, so we're going to call that 16 pounds. Okay, so 2 gallons. Okay, so what we need to do is set up some sort of an equation, okay, where we're going to get foot-pounds. So we need this to be our pounds because our dx, remember, is feet, right? The dx part is the feet. So again, it's like lift the bucket a little bit, but now we have a little less rope, right? So that first foot we raised the bucket, it was heavier at the beginning of that first foot than at the end of that first foot, right? We'll break it down into 6 inches or 1 inch or whatever, right? There's always just a little less rope. So again, that's that dx. Now, you might call it dy. If we're lifting it vertically, you might think of this as more as a y-axis. Doesn't matter. You can use any letter you want. We usually just use x. Okay? All right. So we need an equation here for pounds. Well, where do the pounds come from? It comes from the bucket plus the water plus the rope. Right? Those all weigh something. Right? The bucket plus the water plus the rope. We need to get the weight of those. Now, is the bucket changing? 5 pounds. Is the water changing? No. 16 pounds. Is the rope changing? Yes. So we need to get the rope's weight relative to the distance that it's been pulled up. In other words, there's going to be an x in it. X is the distance it's been pulled up. Okay? So when we've pulled the bucket up to here, this is going to be x right here. And this is going to be 20 minus x right here. Does that make sense? X in this case, x in this problem is how far the bucket has been pulled up. So when the bucket's at the bottom, x needs to be 0. Okay? So how much rope am I lifting? How many feet of rope am I lifting? The way I've written it right over here. No. Well, at the beginning, when x is 0, yeah, 20 feet. But what about when x is 5? How much rope am I lifting? 15 feet. When x is 7, how much rope am I lifting? 13 feet. So how much rope am I lifting at any given time? 20 minus x. That's why I just drew that there. Yeah. 20 minus x is the amount of rope I'm lifting at any given time. That's feet, though. That's not pounds. Okay, that's not pounds. I need it to be pounds. To go into this equation here, to go into my integral, I need it to be pounds. So I have 20 minus x feet of rope. Okay? The rope weighs 1.6 pounds for 20 feet. So what's 1.6 divided by 20? That'd be pounds per foot, right? What's 1.6 divided by 20? 0.08. Doesn't that give me pounds? 0.08 times 20 minus x would give me pounds of rope. There's my integral right there. We basically, there is no formula for this other than the formula here was pounds, but it was the force equation from Hooke's law. That gave us pounds of force in the spring problem. Okay? So that's how we got pounds. In the rope bucket problem, we have to just build the equation. We got to say, okay, in this integral, we want pounds to be in there. The weight that I'm lifting. I'm lifting the bucket, I'm lifting the water, and I'm lifting the rope. The bucket's not changing, the rope's not changing, or excuse me, the bucket's not changing, the water's not changing, but the rope is changing. In a linear fashion. Okay, 0.08 pounds for every foot. Now, if that bothers you to come up with this, oh, and by the way, then what are we lifting, what are we putting in for these numbers right here? Remember, because those numbers have to match that variable right there, right? X is feet of rope that I'm lifting. That's why we have to have X be this. We can't have X be the amount of rope here, okay? Because we'd actually had to go 20 minus 0 then, right? We're starting with 0 amount of rope lifted, or 0 distance lifted, and ending with 20. So 0 to 20 is correct, okay? All right, now type that into your calculator and let's see what we get here. Now I'm going to show you another way we could have come up with that rope. This might be, you might be more comfortable with doing it this way. Since it is a linear relationship, we could just get a couple of points and do a point slope form if you want. Some of you that might be preferable. What are you getting? 436 units. What? What are the units? Foot-pounds of work. 436 foot-pounds of work. Now, if we would have just ignored the rope, if this would have been physics class, we'd have taken 5 plus 16. We'd have said we got 21 pounds that we're lifting for 20 feet. What's 21 times 20? It's 21 times 20. 420. So in physics class, this problem, you would say there's 420 foot-pounds of work. There's a little more because we're lifting the rope. So there's a little more work involved than what the physics formula would say. Okay? Now, and if it just ignored the fact that the rope was getting less and it just did 1.6, right, then you could do 22.6 times 20. And to get closer, what's 22.6? Because the rope weighed 1.6 pounds. Right? So let's just pretend we ignored that it was getting less. So that'd be 22.6 times 20. What is that? 400 how much? 452 foot-pounds. Well, we know it didn't take that much work because we weren't lifting 1.6 pounds the whole time because the rope was getting less. So we know it's in between there somewhere, and that's what we ended up with. Okay? All right. Now, here would have been an alternative for how you could have got the rope. You could have done this. You could have said X You got to understand, though, that X is how much you've lifted it, okay? And then this be the pounds of rope right here, and kind of like an X and Y, okay? So when you've lifted 0, how many pounds of rope do you have? 1.6. And when you've lifted it 20, how many pounds of rope do you have? 0. So you could have said, okay, there's 2 points. There's like an X and a Y. Now I could do the slope, right? What's the slope? Well, you subtract the Y's. 1.6 minus 0. 0 minus 20. So that would be 1.6 over negative 20, which is negative 0.08, right? So that'd give me a slope of negative 0.08. And now I can write my equation, right? Negative 0.08 is the slope. And then put in one of these points. This would be an easiest one to plug in. So we'd have X minus 0 plus 1.6. See how I did that? I just said, okay, this thing is changing. It starts, when X is 0, it starts this many pounds. And when X ends, wherever I'm done lifting, then I'll have this many pounds, right? And look at this equation. If I write this out, that would be negative 0.08x plus 1.6. What do you suppose would happen if I distributed right here? 0.08 times 20 would be 1.6 minus 0.08x. Same equation, right? Same equation. So you can do it this way by saying, well, how much rope am I lifting? I'm lifting 20 minus x. And what is the weight of the rope? It's 0.08 pounds per foot. Feet cancel. I get pounds. You can do it that way. Maybe this makes more sense. Okay, you got changing quantity. The key is it's changing in a linear fashion. So you can just do 2 points and go from there. Okay, let's try that with this one. Okay, so now when we pull the bucket up, it's leaking. Okay, now it's leaking, and so now it's empty when it gets to the top. Okay, so again, bucket plus water plus rope. That's going to be pounds we're talking about. Okay, we want the pounds of those things. Well, the bucket, does that change? No. The rope, we already did. 0.08 times 20 minus x. What about the water? Well, again, we can do it 2 different ways. We can say, okay, how much distance is there? How many pounds per foot is it losing? Because that's basically, well, again, isn't it 20 minus x again? Isn't that how much, right, we have? And then what's it losing? Well, it started out having 16 pounds, but it lost 16 pounds of water over how much distance? 20 feet. Right, which is 0.8, negative 0.8, right? So we can do that. But again, so we could write our equation that way. Or we could just say, all right, here is the feet. When there is 0, when x is 0, how many pounds of water do we have? When we haven't lifted the bucket at all, there's 16 pounds. Once we've lifted it 20, now sometimes it doesn't say the bucket's empty at the top. Sometimes they say it's half empty, right? Well, then you'd put a what here? You put an 8 here. But this time they said it's empty. So there's no water, right? And so we can do our equation. So we can do our slope, 16, do the y first. Yeah, 16 minus 0 here. And then the bottom would be 0 minus 20. Okay, so subtract the y's, subtract the x's. So we get negative 0.8. And then we can write our equation, negative 0.8. X minus 0 plus 16, which is just y equals negative 0.8x plus 16. So, negative 0.8x plus 16. Okay? But again, we could have had the same thing. We could have just said 0.8 is how much water is going out, and then times 20 minus X, right? 20 minus X is how much is left, and there's 0.8 pounds per foot of water that's going in. So either way, it's the same equation. Okay, and then we go 0 to 20 again with that. So type that in your calculator to see how much different. What would you expect? Less or more than what we had before? Less, because we've got less because we're losing water weight. So we'd expect a smaller answer. What do we get? And yeah, this could have been negative 0.08x plus, I think it was 1.6. Was that? How much? 276. Okay. So, wow, that's quite a bit. Makes sense, though. That was most of the weight. Most of the weight was the water weight. Okay? All right. So, excuse me. So, that is the two types of problems we want to deal with. Okay? Now, you get into Calc 2, is typically where the work things. This is not, you notice we haven't skipped any work problems in the packets, right? We haven't skipped any of those because it's not on the AP test. Won't be on our final. It's going to be on our quiz next week. Okay, for sure there'll be one of these, if not two, right? If there's one, it'll be either a spring or a rope bucket, or there could be two. It could be one of each. Okay, so you got to be able to do those two types of problems. Now the third type of problem, and we're not going to get into this here today, but it would be, if you go to a gas station, you pump gas. That gas is not in that, that little tank where the numbers spin and stuff, or the little, the gas is not in that. You knew that, right? Because that'd go empty in a hurry. Where's the gas? It's underneath the ground, right? There's big tanks underneath the ground that they put the gas in. Okay. And so it'd be a situation like this, where this would be the ground level, right? This would be ground level right here, and then 4 feet high, about 4 feet off the ground or so, would be your pump. And there is a motor in there that is pumping this from the tank up to here. Okay, so the question, what's that? I suppose it was a gas motor. How about that? It's got plenty in the tank there, right? So the question would be, and so many horsepower can, do so much work, right? That would be the thing. So how big of a motor, what do you need to be able to pump this? How much work does it take to pump gas up this distance? Well, it's going to vary because the farther it has to travel, right? Some of the gas doesn't have to travel as far to get to there as some of the rest of it. So the distance is variable in this case, as opposed to the weight, the force, okay? And so that's what changes in this problem, okay? So the dy part of it actually comes in there, okay? So that would be kind of the next level of problem, but we're not going to do that one, but I wanted you to see it, please. Okay? All right, so the homework is on your in your book, actually. It's the 7.3 line. Okay, so I'm trying to leave you some work time to get something done. I tried to do that yesterday. We had the fire drill, which took some of it. We got back to the fire drill. It was 15 minutes or so, and some of you didn't even crack open the LH packet for 15 minutes. You just sat here. I don't know what you were talking about, but you talked about a lot of different things. But it didn't have anything to do with calculus. So, and then we came in today, and some of you sounded like you didn't have much of a clue what was going on with the shell method or the dishwasher or whatever. So it's going to be a problem on the quiz next week. So, we kind of joked around about the 80-20 thing, but, I was semi-serious about, hey, let's try to keep the homework a little lighter, getting towards the end of your senior year. You don't have to spend 3 hours outside of class, but, 10 minutes wouldn't be bad. 15 minutes wouldn't be bad. We've got probably over almost 25 right now, okay? So I'd like to see you try to get some of this done. We're gonna move on to another new thing tomorrow, so my expectation is you'll be, have a good handle on these, especially if you don't come in and see me in the morning or something or ask questions. I don't spend a lot of time going over it. A little bit tomorrow maybe, but not a lot, okay? So this is a good 25 minutes to get some of that done, check your answers, ask me questions, okay?